Is going to talk about AI/ML techniques for model-independent cosmological.
I'll give you a warning at 10 minutes. Perfect. Thank you.
Am I audible? At the back? Okay, perfect. Okay, so I know what everyone is thinking is just another ML talk, but I'm not here to oversell buzzwords. Rather, I just want to share my humble explorations of machine learning in a cosmological context. So, hello everyone. I'm a PhD student at the Indian Statistical Institute in Kolkata, and in fact, I'm on the brink of submitting my thesis, and I am on the postdoc hunt. And I'm very thankful to the organizers for this wonderful opportunity. So the central message that I want to convey through my presentation today is that machine learning has proven useful in cosmology, but it also changes how assumptions enter our inference process. And as a result of that, rather intuitively, physical insight and physical validation becomes more important and not less. And that is something that I want to describe through examples of my work. So of course, this needs no introduction thanks to my previous speakers. So the lambda CDM model has been extremely successful in explaining a wide variety of observations. But of course, when you look closely and you compare precision data sets, you come up with problems. Of course, tensions have been kind of a central theme of my PhD work. And in my limited understanding, I feel that there are three different ways that you can approach these issues. So the first is going beyond lambda CDM. The second is to wait for new data or data from novel probes, for example, gravitational waves or even 21 centimeter observations. And the third approach is to revisit our analysis pipelines in as model independent ways as possible. And this third approach is what I'm going to focus on today. So, at a very abstract level, cosmology is an inverse problem in the sense that we start from certain initial conditions, we evolve them using some complicated physics, and whatever predictions we get, we compare them to observations. But what you actually want is, the reality is you have noisy data. You have actual noisy correlated data sets, and you are trying to infer the underlying smooth description of the universe. Now, this process is becoming more and more difficult because our data are becoming high dimensional and our models are becoming more and more complicated. So machine learning is useful in such contexts because it's a numerical tool which is based on implicit assumptions. And these assumptions are learned directly from the data. So it removes the need to explicitly model your cosmology parametrically. But with this increased flexibility, you also need to be very careful about how you validate these predictions, because such models will always give you some prediction. It's very important to understand whether those make sense from a physics point of view. So that is going to be the central theme of what I'm going to present. So, I think some of you have already seen this, but I really like this code because in traditional cosmology, you write assumptions in priors, likelihoods, and functional forms. So we know where they are. We can argue about them, but we know where they are. But in machine learning, these assumptions don't vanish. They just move behind architectures, loss functions, and hyperparameters. And that matters a lot for inference. So just to concretize things a bit, for example, the data sets that we mostly consider in cosmology are, let's say, the CMB, BAO, and supernovae. These are noisy correlated data sets. But what do you actually want? You want these. You want the expansion history. You want distances as a function of redshift. You want fields, etc. Now, there are two ways to do this. You can either assume some functional forms for these and then fit it to the data. Those are parametric approaches. Or you can use non-parametric approaches which try to learn these forms directly from the data. So machine learning algorithms belong mostly to this second category. So the particular class of models that I'll be discussing today are deep learning networks. Now, without going into the technical details of this, what you need to understand is these are called universal function approximators, in the sense that they have the capability to mimic any function given enough data and flexibility. And that is why it's very suited for problems like late time data-driven reconstruction in cosmology. Now, of course, we are not the first ones to use these networks in the context of reconstruction, but at the time when we were looking at this problem, there were some issues in the literature that we found to be more or less generic. For example, the reconstruction that you get, it's not unique in the sense that it varies from different architecture to architecture. It even varies from different, from one training run to the other. So there's some sort of uniqueness needs to be there when you're learning from data. Also, there were some underfitting and overfitting issues. People usually didn't consider the covariance matrix in the data. And of course, the approaches at that time were not reliably extrapolated beyond the redshift range. So we came up with sort of a new sort of learning algorithm to hopefully overcome some of these issues. And this we did with, in collaboration with machine learning experts at my institute. The code is now public. And in the remaining time that I have, what I want to do is, I want to share what this code does differently, how we physically validate it, which is very important, and some cosmological applications of it. So this is more or less the overall structure of the algorithm, but without going into the details, I'll tell you the two defining features of ladder. So the first feature is it uses LSTM networks. So LSTM networks are long short-term memory networks. These are very well suited for sequential data, which is the sort of data set that we have. Oh, I forgot to mention the data that we use. So we are considering apparent magnitude data from type 1a supernovae from the Pantheon compilation and its associated covariance matrix. That's our data set. So we use LSTM networks because it has a sequential nature to it. We also use a KL divergence metric in the loss function. Why do we do this? Because our, this algorithm predicts not just the mean values, but also the projected uncertainties. So the KL divergence metric is really good as a loss function in that sense. So all well and good. We have a fancy algorithm. It's kind of fitting the data very nicely, but doesn't make sense. To understand that, we did some physical validation tests. And this is the main thing that I want to take some time on. So you can have various different architectures of your networks, right? So we impose certain metrics. For example, we expect the reconstruction to be smooth. We expect the reconstruction to be monotonic, for example. So we compared various different architectures on these metrics, and the best performing one is what we chose as ladder. Also, as one more thing. Since we are using I said we are using LSTM networks. The other thing that ladder does is usually a machine learning network learns one data point at a time. Here it doesn't do that. It learns on local Gaussian chunks of the data. So in that sense, it learns the local as well as the global nature of the data. So that is another defining feature of our algorithm. So that is the important point. If you do these if you impose these physical conditions on your predictions, then you can more or less confidently say that your predictions are physically viable.
So what is the coherence length to choose between small scale and the large scale that you correlate, that you allow for learning?
Right. So this is not GP. This is absolutely free weights. So there's no correlation length that we are taking in the sense. Oh, you mean by you mean the? Oh, okay. No. So it's the Spearman correlation coefficient that we use, and the best performing one is the one we take. Right. So yeah, so this is my general approach to machine learning in the sense that as I said, any network will give you some predictions. The question is, are they correct or not? So that is why you need to be very, very careful about how you physically validate your predictions. Otherwise, it makes no sense. So, okay, great. So now we have a fancy algorithm and we have hopefully validated it physically. What can we do? Well, the first thing that we need to do is, how does it behave out of sample? So it has been trained with the Pantheon supernovae compilation, right? So we asked it, well, can you predict Pantheon plus, something that ladder has never seen? And visually you see, well, it does quite a good job. And when you quantify it, you constrain certain cosmological models with these predicted data sets and the original data sets. They seem to be consistent to within 1 sigma, which tells us two things. One, ladder generalizes quite well out of sample. Two, ladder can be used as a model independent test for checking consistency between similar data sets. Now, these data sets might have completely different systematics and analysis pipeline. That's fine. But it's a tool to check whether two different, let's say, supernovae data sets, how consistent they are in a model independent way. So that's the first, yes?
That test can how much overlap there is between the Pantheon and Pantheon plus samples and analysis.
Sorry, can you?
There's a significant overlap in the sample and analysis.
Yeah, absolutely. That's true.
You have like an independent test.
Yeah. So when we are predicting on Pantheon plus, we only take those redshifts that are not in Pantheon. Yeah, we do that.
But is it possible anyway that two samples, they are completely defined systematics. You learn your thing with one data, and then you are predicting something which is completely defined systematic, but you are getting the results correctly. How is this
So the
sort of
conclusion,
magic?
yeah, that's very true. So there are two ways to look at this. One, if you assume that the systematics in the two data sets are both correct, let's say, then that means the ladder is a good method. This is one. It will support my viewpoint. On the other hand, I'm saying let's say ladder is correct. Ladder is a very good tool, and if it is showing that they are consistent, that means these two systematics are also consistent.
No, what do you mean by consistent?
Consistent, from a, what I'm trying to do is I'm trying to learn the expansion history of the universe, so to say. So when one compilation gives you some data, it is ultimately trying to do that using some pipeline. This is using some other pipeline. And I'm saying these two are converging. So effectively, you can say that these two compilations, whatever their systematics and analysis pipelines are, they're consistent. They might not be the same, but they're consistent. And this is a tool to show that in a model independent way. If they don't match, then we can raise questions, well, are those systematics similar or not? Yes. So we are not saying,
So you are,
yes.
you are practically is an extrapolation in the range where you have not seen the data.
Not extrapolation, I would say interpolation because
So Pantheon plus goes far.
it does, but still we are training on what? We are training on these red points. So this is Pantheon plus is still in that range.
I was saying this. So you are saying that only in the overlapping relationships you use.
No, so we have trained ladder with the red data set, and then we are predicting at the blue redshifts.
And the extra part you are predicting correctly.
Yeah.
So that's an extrapolation.
No, because these data points actually right. Yes, because that's very low
That's the
redshift.
model,
Yeah.
Whatever model of cosmology you have with the low redshift.
Yes.
And whatever systematic you have low redshift, they are same. The extrapolation is correct.
Yeah, absolutely. Okay, so that's okay. So that's the first application that I wanted to show. The second thing is okay. So apart from CMB, BAO, and yes. Oh, sorry. Thank you. So apart from CMB, BAO, and supernovae, there are other data sets that you can use to constrain cosmological models or do cosmology with. So an example of that is gamma ray bursts. Now, gamma ray bursts are high redshift data sets with which you can do cosmology only if you are able to calibrate it correctly. Now, since they are high redshift, since they are sparse in redshift, and since the errors are heteroscedastic, it's very difficult to calibrate them using the standard cosmic distance ladder method. So usually what people do is they assume some cosmological model to arrive at a calibrated GRB sample. But we were able to show that using ladder, which doesn't assume any cosmological model, you can arrive at a uniquely calibrated GRB data set and you can do cosmology with it. So we did that. I'll not get into the details of how. I welcome you to look at the paper and have a look. But once we had that, we constrained, again, lambda CDM, WCDM, some representative models with this ladder calibrated GRB dataset and lambda CDM calibrated GRB dataset. And we saw that the constraints don't vary much. But ladder calibrated GRB dataset is model independent and it gives you a uniquely calibrated GRB dataset. So this is another application where I'm trying to show that tools like ladder can help you constrain, help you calibrate high redshift datasets so that you can do serious cosmology with it. So that's the second application I wanted to share. This third, okay, very quickly. Third application. So BAO measurements are basically angular measurements on the sky, right? And you can find distance to those BAO features if you know the intrinsic length of those angular measurements. Now, those intrinsic lengths can be inferred in the context of a cosmological model from the CMB. So you assume a cosmological model, you know how big those acoustic scales are. The thing is, so that's BAO. On the other hand, ladder predicts apparent magnitudes of supernovae, right? Now, in order to get distances from supernovae, you need to impose some sort of a low redshift astrophysical bound on the absolute magnitude. So what we can do is, we can cross-correlate these BAO redshifts with ladder predictions and then impose either of these distance scales. We can do that. Once we do that, for either of the distance scales, you can arrive at a data-driven MBRD parameter space, which is what I'm showing here. And we did this for 2D bow and 3D bow data sets. We saw that for 2D bow data sets, these contours match. For 3D bow, they do not. This is not a new result. People know this. We know there's a problem in 3D bow when you impose these different distance scales. My point is, ladder provides, again, a model-independent tool to unearth this problem. So what I'm trying to say is machine learning can help unearth certain inconsistencies in existing data sets in this way. So that's the main point that I want to drive home. And you can take this one step further. What you can do is, when we usually constrain cosmological models, we typically take supernovae, bow, and CMB. Now, as I said, you can impose either distance scale for bow, right? Now, in the standard scenario, you impose this distance scale assuming a cosmological model from the CMB. What if you don't do that? What if you impose a late time astrophysical prior on MB and recalibrate bow, right? If you do that, and then you do your usual MCMC analysis, we see that there's sort of a in-plane shift in the H0 S8 contour in such a way that both tensions seem to be somewhat relaxed, somewhat. Does this mean we have solved everything? I mean, both tensions are solved within lambda CDM with current data sets? No, that's not the point. The point is, you need to understand that these interrelationships between data sets, these dictate very strongly how your final constraints look. And tools like ladder can help you test alternative calibrations of these data sets, let's say to decouple them and see how they affect cosmological parameters. So we are currently looking at how the other parameters change and the whole implications of this, but this is just a demonstration that these calibration changes can help shift your cosmological parameters. I will skip this in the interest of time. So to wrap up, my main message is that machine learning shifts assumptions from explicit to implicit, and that is why it is very important that you test your predictions using fundamental physical intuitions, fundamental physical, bounds, rather than just blindly believing whatever your machine learning model gives you. So the danger with machine learning is not that it's flexible. I mean, the danger with machine learning is that it can give you predictions which look correct even when they're not. So that is why the only safeguard is to use certain physical validation tests. So that's the main takeaway I would like you to take away from this presentation. Currently I'm working on trying to extend ladder to other data sets, other applications. Mostly in my PhD work, I've mostly dealt with late time observations. So I'm trying to see how such machine learning applications can be used in the early universe, so to say. And I will just end with this. This is just to flash. There's nothing to do with machine learning. This is some of our recent work where we have forecasted on interacting dark energy, dark matter models in the context of future surveys from SK and Euclid. I just wanted to flash this before I end. Yeah, thank you.